Hi there, I hope you are well. Today lesson about torsion part 2. But first, we are going to review the topics in torsion part 1 that I taught to you in the previous video. Started. Let us review what is shaft. Shafts are the machine elements which are used to transmit power in machine, and they may be solid, as this figure, hollow, and tapered, having circular, square, rectangular, or other types sections like this figure. And what is torsion? We said that torsion is taking place when a force on a rod is applied to twist or turn the rod. And the amount of twisting denoted by the angle of twist theta. It depends on four things, very important four things. Number one, applied torque, which is force times radius of the shaft, length of the rod or beam L, modulus of rigidity or shear modulus of rigidity, G capital, don't forget G capital equals tau over gamma, and torsion constant J. J is the polar moment of inertia of the section, and R is the outer radius of the rod or shaft. So angle of twist, as we said before, theta in radian equals TL over GJ, where TL, G, and J and D are as shown here. The units you need to use in your calculation, please. Then torsional shearing stress, tau. For a solid or hollow circular shaft subjected to a twisting moment T, the torsional shearing stress tau at a distant rho from the center of the shaft is tau equals T rho over J for any distance from the center of the shaft, while the maximum tau maximum, will be on the outer or the radius of the shaft, which is equals TR over J. We said before J is the polar moment of inertia of the section. For solid cylindrical shaft, J is pi over 32 d to power 4, and tau max 16 times t over pi d to the power pi d cube. And for hollow cylindrical shaft, as shown in this equation. So, and we have said that power transmitted by the shaft as well. So, in many practical applications, shafts are used to transmit power, P, and power equals torque times omega, where T is the torque and omega is the angular speed measured in radian per unit time. And if the shaft rotating with the frequency of f revolutions per unit time, so omega equals 2 pi f, and we have power equals torque times 2 times pi times frequency. Thus, the torque can be expressed as torque equals power over 2 times pi frequency. And please keep in mind the angle of a twist, theta equals TL over GJ in radian. If you use this TL GJ, you will get theta in radian. But theta equals TL over GJ times 57.3. If you multiply this side by 57.3, you will get theta in degree. Otherwise, you can multiply theta by pi over 180 degree equals TL over GJ in degree. So theta, this left hand side, multiplied by pi over 180 degree equals TL over GJ in degree. And keep in mind that pi over 180 degree equals 1 over 57.3. Solution of problem number 309, page 83. An aluminium shaft with a constant diameter of 50 millimeter is loaded by torques applied to gears attached to it, as shown in figure 2. This gear system, gear A, B, C, D, with torque on each one, as shown in figure. Using G equals 28 gigapascal, determined the relative angle of twist of gear D relative to gear A. So from D to A, the change or the angle of twist. So to start the solution, given D equals 50, torque as in figure 2, 600, 900, 1100, 800, and G, the modulus of rigidity, 28 gigapascal. So from this given variable, we need to calculate theta, but keep in mind theta from D to A. So how to solve this question or problem? First of all, determine theta, keep in mind, of gear D relative to gear A. So there is a sign convention to solve this problem. Clockwise torque on the gears is plus, like this, any clockwise plus, or this double-headed arrow in this direction. Otherwise, counterclockwise torque is negative. This is counterclockwise, or the double-headed arrow from right to left. So we need to draw the torque diagram from gear D to gear A as required. So first of all, this is the free body diagram of the figure of the problem. So how to draw the torque diagram depending on this sign convention. First of all, we put a line, horizontal line of the torque diagram. Then we start from D. Here is 800. Here is 800. We will start with this 800 torque, which is on this, in this direction, which is clockwise, and it is positive. So from D to A, so we start from D, it's positive 800. Then from D to C, we don't have anything, we put a horizontal line. At C, we have 1100 Newton meter torque, which is counterclockwise and negative. Then from C to B, nothing. So 1100 take away 800, it will be here 300. So 1100 minus 800, it's 300. Then 900 positive goes up, so it is 600 here. Then from B to A, nothing, horizontal arrow. Then at A, we have 600 counterclockwise minus, bring you back to 0. So in these two parts of the torque diagram, positive torque, and in this part is negative 300, and here's positive 800, here positive 600, here minus 300 torque. So as shown in this figure as well. So theta required TL over JG. Rotation of D relative to A. So theta D relative to A equals 1 over JG, which is a constant for all the shaft, summation TL. This is 1 over J, which is solid, pi over 32, 50 to power 4 to the power 4, times G, which is 28,000 megapascal. All times the summation. 800 by 2 minus 300 by 3 plus 600 by 2. Multiply by 100, which is the meter to millimeter, or it's تحويل وحدات, unit compatibility. Then theta for D to A equals 0.1106 radian. Multiply this by 57.3, we get theta D to A equals 6.34 degree. So for this part 2 of torsion, flange bolt couplings. Look at this figure. There is 3 parts. This is flanged bolt couplings in the 3D, and this is the view of this plan, and this is the component of the flange bolt couplings names: driven shaft, key, hub, and so on. So in shafts connection called flange bolt couplings, as shown in figure 3, the torque is transmitted by the shearing force P created in the bolts that is assumed to be uniformly distributed. So on each bolt we have a shearing force P equals area times stress, shearing stress, equals area of the bolts is pi over 4 d squared times tau. So shearing force equal for any number of bolts. So here is not only one bolt, here is 1, 2, 3, 4, 5, 6. So for any number of bolts n, 6, 10, 11, 8, the torque capacity of the coupling is expressed by, so it's a summation torque equals P force times R times N, and equals pi d squared over 4 times tau R N. This is equation 3-4 in your text. If a coupling has two if a coupling has two concentric rows, if a coupling has two concentric rows of bolts, the torque capacity is, as shown in this figure, torque is summation of the two rows. So P1 R1 N1 plus P2 R2 N2. This is equation 3-5 in your textbook, where the subscript 1 refers to the first row per outer circle, and the subscript 2 refer to bolts on the inner circle, as shown in figure. For a rigid flange, the shear deformations in the bolts are proportional to the radial distance from the shaft axis. So the shearing strain gamma are related by, and don't forget gamma equals shearing deformation over original length. So the shearing strain gamma are related by gamma over R1 equals gamma 1 over R1 equals gamma 2 over R2, equation 3.5. Sorry, not question, this is question A. So using Hooke's law for shear, G equals tau over gamma. We have, as we said before, G equals tau over gamma. So using Hooke's law for shear, so gamma here equals tau over G. So tau 1 over G1 R1 equals tau 2 over G2 times R2. Or replacing tau, which is force over area, to be this equation. But if the bolts on the two circles have the same area, same bolts, let us say bolts number 6, number 10. So the area of the bolts in each row is the same. Area 1 equals area 2. And if the bolts are made of the same material, for example, steel, aluminum, so G1 equals to G2. The relation between P1 and P2 reduces to this P1 over R1 equals P2 over R2. Let us solve a problem. Solution to problem number 326, page 82. A flanged bolt coupling consists of 10 20 mm diameter bolts spaced evenly around a bolt circle 400 mm in diameter. Determine the torque capacity of the coupling if the allowable shearing stress in the bolts is 40 megapascal. It is same problem number 326, but with different variables, different figures. So this is the figure. So given n equal 10, d 20 millimeter, r is 400 for the diameter divided by 2 is 200 millimeter, and tau is 40 megapascal. To solve this problem, torque equal PRN, so it's A tau Rn, and it's 1 over 4 pi d squared tau Rn. So torque by 1 over 4 pi 20 is the diameter, square 40 is the tau, R is 200, and 10 is the number of bolts. You can count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, or it's said here consists of 10, and then torque equals this because the torque is wanted in this problem. And go to pages 87 to 90 in your textbook. Solution to problem, another one. A flanged bolt coupling consists of 8 10 mm diameter steel bolts on a bolt circle 400 mm in diameter, and 6 10 mm diameter steel bolts on a concentric bolt circle 300 mm in diameter, as shown in figure 6. So two circles, outer and inner. What torque can be applied without exceeding a shearing stress of 60 megapascal in the bolts? So this is the given N1 D1 R1, because it's two rows, and 2 they said, and 6, and 1 is 8 10 millimeter, and here and 6 10 millimeter. So D2, sorry, here is 10 millimeter. This is R2, not R1, sorry. Okay, so R1 is 200 millimeter and R2 is 150 millimeter. And the maximum shearing stress is 60 megapascal. We don't need to exceed the shearing stress. So, and the required is torque. So for one bolt in the outer circle, we will apply the allowable shearing stress. So P1 equal A tau and P1 equal 1500 tau Newton. For one bolt in the inner circle, because we applied his shearing stress for the first row, for the second row we'll do the next equation, which is P1 over R1 equals P2 over R2. From this we'll calculate P2 equal to 1125 pi n. Then we do summation, torque equal P1 R1 N1 plus P2 R2 N2, and we put all the variables here, and we get torque equals 10.72 kilonewton meter. So self-study or independent study, you need to do problems number 327, 328, 329, and 330 are required as a homework for your kind attention and further action. So upload or turn in your solution as a JPG or PDF. Go to pages 87 to 90 in your textbook, Strength of Materials by Singer and Python. Thank you very much. كان معكم دكتور زهير كاظم جهانجير، مدرس مادة مقاومة المواد، المرحلة الثانية في قسم هندسة المواد المائية، كلية الهندسة، جامعة بغداد. Thank you.